interphone talking about a hole in the cabin, and he tried to communicate with them multiple times to no avail. He wasn't sure whether they were okay and whether they could even hear them. Meanwhile, the flight attendants were trying to communicate with the pilots, but the noise was so loud in the cabin that they didn't know whether the pilots answered or if they were even okay. The pilots had no idea what was happening in the cabin, and the flight attendants had no idea what was happening on the flight deck. To quote the captain, it was an explosive experience. The first officer said it was chaos. Back in the cabin, the flight attendant saw 5 empty seats next to a gaping hole in row 26 and believed multiple passengers had been lost. From an interview, I look down the aisle and I see the mom of the child by the window. The mom was on the floor just screaming like agony, and she was shaking. I was holding her. I said, "What's going on? What's happening?" And she just says, "I was holding my son, and I think my son blew out." That's when I lift up my head and I saw the hole and I just started shaking. It wasn't until the crew deplaned that they learned they didn't lose a single passenger, that all crew members were accounted for. Throughout this meeting, you'll hear more about what it was like on board Flight 1282 that day. I think what's most inspiring to me, and I would imagine this entire board, is amidst absolute chaos, and I imagine fear, the crew members were laser focused on the safety of their passengers. Using supplemental oxygen, the flight attendants ran up and down the aisle to check on passengers, never forgetting the most vulnerable on board, 3 lap children and 4 unaccompanied minors, one of whom was just 6 years old. He had turned 6 just about a week before, and it was his first time flying. I hope everyone in this room or watching online takes away a newfound appreciation and respect for the men and women who protect us in the air and on the ground. Above all, these highly trained professionals are there for our safety. Safety. That's the promise the Flight 1282 crew delivered on. Despite the harrowing circumstances, every single crew member performed their safety duties with the highest degree of professionalism and competence, remaining calm in the most turbulent of times. They are why all 177 souls on board Alaska Airlines Flight 1282 deplaned safely at the gate. And I want to take a moment on behalf of the entire agency to commend the entire crew. This doesn't just happen. Every single crew member we interviewed credited their training. We at the NTSB examine training in every accident we investigate, in every transportation mode. Why? Because it can and often does make the difference between life and death. When every second counts, as it did on Flight 1282, training to the point of muscle memory is paramount. In this case, the crew knew precisely what to do. They acted without hesitation, and it saved lives. And yet the crew shouldn't have had to be heroes, because this accident never should have happened. Since this accident occurred, there's been a lot of focus on human error, on the actions of 1 or 2 individual Boeing employees. Let me be clear. An accident like this does not happen because of an individual or even a group of individuals. Aviation is much more resilient than that. An accident like this only happens when there are multiple system failures. This is from the draft NTSB report we'll soon discuss. Within a robust system, the introduction of a single error is almost never the only cause of an accident. Rather, several barriers of defense must fail for the error to lead to an accident. Several barriers of defense must fail for the error to lead to an accident. The truth is, there was a long chain of events that led to the door plug departure. Problems were identified in numerous Boeing internal audits across production lines, employee speak-up reports, quality alerts, and regulatory compliance issues. In other words, the safety deficiencies that led to this accident should have been evident to Boeing and to the FAA. This time, it was missing bolts securing the door plug, but the same safety deficiencies that led to this accident could just as easily have led to other manufacturing quality escapes and perhaps other accidents, which leads me to the ultimate purpose of our investigation: to inform safety recommendations that, once implemented, will help Boeing close the systemic gaps that led to this accident, will help strengthen each barrier of defense against quality escapes, so that every airplane leaving a Boeing factory is safe to transport the most precious thing imaginable, human life. Our job is to make recommendations to prevent accidents like this from recurring. Following the accident, Boeing rolled out its safety and quality plan, which has the same goal. Will Boeing's plan, in fact, prevent accidents like this from reoccurring? Are there still gaps? We discussed some of those gaps at the hearing last August, including the need for continued development of Boeing's safety management system and improved safety culture, which they themselves recognize and have done a lot of work on. How do Boeing and FAA know the key performance indicators to measure the health of Boeing's production lines are the right ones for safety? Before the accident, multiple tiers of Boeing leadership routinely assessed quality control metrics, such as non-conformances, quality escapes, and regulatory compliance issues. What has changed? Are the processes they developed since the accident going to prevent, or at a minimum, detect the next manufacturing issue before the airplane leaves the factory, before there's an accident? I do want to commend and thank Kelly Ortberg for his safety leadership. He has made himself the accountable safety executive, and he has done a lot of work at Boeing since this accident. We've had several great discussions focused on safety since he came on board. He has a lot of work cut out for him, a lot of challenges to address, and that is going to take time. I visited Boeing and Spirit Aerosystems, my colleagues did as well, just a few weeks ago, to see some of the changes they've made since this accident occurred. I'm thankful for their progress, but you'll hear today that more can and should be done. When it comes to safety, the NTSB sets a high bar. We've been unequivocal when it comes to demanding excellence in transportation safety and demanding excellence from Boeing. Lives depend on it. Boeing is a cornerstone of American aviation. It is a pillar of American manufacturing, supporting more than 170,000 direct jobs and an estimated 1.6 million indirect jobs around the globe. I believe Boeing, Spirit, and the FAA will take the lessons learned from this accident to heart and again become a world leader on aviation safety. Please know that I, all the board members, the entire team at NTSB are here as a resource, not to help you meet the high expectations that we all have for you, but to actually exceed them. With that said, this isn't all on Boeing or Spirit. I have lots of questions about where FAA was during all of this. The FAA is the absolute last barrier of defense when it comes to ensuring aviation safety, protecting the more than 1 billion passengers and crew members who fly on U.S. and foreign airlines annually. Appropriate oversight of those they are charged with regulating is critical, and I'm hopeful that with new leadership at DOT and at FAA, that will occur. I believe firmly that change brings about new opportunities for much-needed reform and a renewed commitment to safety, something we've seen from Secretary Duffy since day one. Let's now turn to today's meeting. I want to recognize our Managing Director, Dana Schultz, who will introduce the NTSB team participating in today's meeting. Good morning, Ms. Schultz.
Thank you, and good morning, Chairwoman Hamady and members of the board. My only administrative announcement this morning is for meeting participants to silence their electronic devices at this time. I'll now introduce staff for today's meeting. Unless otherwise noted, staff are from the Office of Aviation Safety. In the front row to my right, Tim LeBaron, Director, Office of Aviation Safety, Doug Brazy, Investigator in Charge, Pacholo Cruz, Manufacturing Records, Nils Johnson, Manufacturing Records, and Dr. Sabrina Woods, Human Performance. In the second row, directly behind me from left to right, Jen Adler, Director, Office of Safety Recommendations and Communications, Tom McMurray, General Counsel, Mike Badinsky, Acting Director, Office of Research and Engineering, Kathy Strong, Report Writer, Captain Star Blum, Operational Factors, and Crookshanks structures. And in the third row, behind me from left to right, Jonathan Hsu, flight data recorder and visuals from the Office of Research and Engineering, Kyle Garner, cockpit voice recorder, flight data recorder, and timer, Office of Research and Engineering, Dr. Matthew Fox, materials, also from the Office of Research and Engineering, Ms. Emily Gibson for cabin safety, Adam Hurray for systems, and Mr. Nathan Hoyt, safety recommendations in the Office of Safety Recommendations and Communications. The presentations will begin with an investigation overview by the investigator in charge, Doug Brazee. Doug?
Thank you, Dana. Good morning, everyone. As the chairwoman mentioned, on January 5, 2024, Alaska Airlines Flight 1282 departed Portland International Airport, Portland, Oregon, destined for Ontario, California. At 5:13 p.m., about 6 minutes after takeoff, the left mid-exit door, or MED plug, opened and departed the airplane, which resulted in a rapid depressurization. While climbing through 14,830 feet, the captain recalled there was a loud bang, and the flight deck door was blown open due to the depressurization which had initiated in the cabin. Both flight crew immediately donned their oxygen masks. They recalled it was very noisy and very difficult to communicate, both among themselves and with cabin crew. They immediately contacted air traffic control and began executing emergency procedures. Meanwhile, in the cabin, the emergency oxygen masks deployed, the cabin crew performed their safety functions and other duties, which included closing the flight deck door, donning oxygen masks so that they could assist passengers, attempting to communicate with the flight crew, but it was so loud they could not hear a response. Assessing the condition in the cabin, issuing instructions, and performing appropriate individual checks on passengers such as the unaccompanied minors. They also prepared the cabin for the emergency landing. The airplane returned to Portland and landed safely about 14 minutes after the MED plug separated. The crew taxied to the gate where aircraft rescue and firefighting personnel and equipment were waiting. A hole in the fuselage was located near rows 25 and 26 where the MED plug had been. The left MED plug was later recovered from a neighborhood backyard. The MED plug is a customer option used in place of an emergency exit for seating configurations that do not require additional exits. It weighs less than an exit door, is less complex, and requires less maintenance. It does not have any handles, and it is not opened or closed during flight operations, nor is it normally opened during the remainder of production. However, the left MED plug on this airplane was opened during the final assembly in Renton to allow access to an area that needed rework to rivets located in the fuselage. Although photographs and witness marks showed that the MED plug's 4 retaining bolts had been previously installed, when the airplane left the Renton facility, those bolts were missing. This slide shows the MED plug and some of its associated hardware. The left image shows a view of the interior side, and the right image shows the exterior side. Next, I'd like to show a video of an exemplar MED plug as it is being installed. It shows a technician as he is tightening 3 of the 4 MED plug bolts. This next series of slides shows how the MED plug operates. In order for the MED plug to open, as it did in the accident or for maintenance, with the 4 bolts removed, it must first move upward and then rotate outboard on its hinges. The purpose of the bolts that were missing are to prevent the MED plug from moving upwards. This diagram is an edge view of selected hardware mounted on the forward side of the MED plug and on the fuselage edge frame. The two bolts that should have been installed on this side of the plug are depicted in white. An identical pair of bolts on the aft side, not depicted, were also missing. Stop fittings, when engaged, prevent the MED plug from moving outward. Each one has a part mounted on the MED plug and one part mounted on the fuselage frame. There are 6 stop fittings on each side of the plug. With the bolts out of place, the MED plug is free to shift upward. If it moves up far enough, the stop fittings disengage. With the stop fittings disengaged, the MED plug is free to rotate outboard on its hinges. Let's go through that sequence one more time. On the left side, the plug is in a closed position. In the center image, it has shifted upward. And in the right image, it has rotated outboard along its hinges. You will hear more information about the MED plug in Mr. Cruz's and Mr. Cruikshank's presentations. The investigation found that these items were not a factor in the accident. All crew members were current and qualified. There were no scheduled or unscheduled maintenance activities with regard to the MED plug since Alaska Airlines took delivery of the airplane. No issues were found with the pre-flight inspection walk-around procedures. And the cabin pressurization system, including its auto-fail indications that occurred on previous flights, did not contribute to the accident and was not symptomatic of a problem with the MED plug. The investigation found several safety issues, including Boeing's documentation, specifically the lack of critical removal documentation or records for the non-routine MED plug work performed during production. A key Boeing business process instructions for parts removals was overly complex and had a history of compliance issues, including unauthorized removal of items. Inadequate training of personnel and ineffective change management strategies in response to a decrease in workforce experience. Incomplete closure of the MED plug without the 4 bolts. Boeing's ineffective corrective actions in response to the history of compliance issues and the FAA's ineffective oversight. Inadequate quality escape mitigation efforts which focused on components or product conformance should also have strategies to address the actions of people performing tasks and mitigate potential human errors. In addition to those manufacturing-related safety issues, we also found a need for review of portable oxygen bottle use design standards, flight deck door operation description in flight crew manuals, additional flight crew training with differing oxygen systems. We are also concerned about procedures and technology to preserve cockpit voice recorder audio and the potential injury for lap-held children during a rapid depressurization. I will discuss some of these issues now. The remainder will be covered by my colleagues in their presentations. The MED plug had shifted upward over time during previous flight cycles, as evidenced by a series of parallel dust and dirt witness marks along the section of its seal contact area on the fuselage. This displacement was too small to be seen by the flight crew from the ground during pre-flight walk-around inspections. The MED plug is not visible from inside the cabin except for its window. It's hidden behind interior panels. 2 of the 4 portable oxygen bottles were used in flight. One flight attendant was unable to open the packaging without improvising a tool, her identification badge, to puncture it. This flight attendant also had trouble uncoiling the tube and donning the mask, choosing instead to hold the mask over her mouth rather than secure it. Although this particular mask a plastic bag with exhalation holes, a metal nose strap, and an elastic head strap met FAA design standards, the difficulties the flight attendant encountered using them suggest that the standards, the mask design, or both do not adequately consider the ease of use. Flight attendant training exercises did not include opening a sealed mask packaging. The mask type shown here and used during the accident is one of two common mask types. The ability for the crew to don masks quickly during an emergency is a safety issue. Staff has proposed one recommendation in this area. The potential risk to lap-held children during a rapid depressurization, severe turbulence, or loss of control is a safety issue. The NTSB has a long-standing history of interest in the safety of lap-held children on board airplanes. For more than 3 decades, we have recommended that the FAA require the use of a child restraint system appropriate to the child's size and weight. However, in response to these recommendations, the FAA has consistently declined to mandate child restraint systems usage for children under the age of 2. Staff has proposed to reiterate recommendations in this area. The accident airplane was equipped with a 2-hour cockpit voice recorder, or CVR. According to Alaska Airlines Flight Operations Manual, flight crews involved in an accident or incident were required, if possible, to pull the CVR circuit breaker as soon as the airplane was secured in order to preserve the audio. However, this procedure was not followed, and by the time maintenance personnel pulled the circuit breaker, the accident flight audio had already been overwritten. Additionally, had the airplane been equipped with a 25-hour cockpit voice recorder, something the NTSB has long recommended, the audio from the accident flight would have been retained. Staff has proposed recommendations in this area. Before I close, I'd like to acknowledge the NTSB staff who participated in the investigation. And also the parties to the investigation. Additionally, numerous safety actions were taken after the accident, some of which we will discuss here today. Up next are presentations covering the issue areas of manufacturing records, human performance, structures, and operational factors. Madam Chairwoman, this concludes my presentation, and now we'll hear from Mr. Cruz about maintenance records.
Mr. Cruz, if you can hold for a second. It is hot in here. We're going to be here for a while. So I do want to invite staff, if you want to take your jackets off. People are more interested in what you're saying than what you're wearing. So feel free, please, be comfortable. It is hot. We will be here for a while, so feel free to do that, okay?
Thank you.
Good morning, Chairwoman Hamidi and members of the board. In staff's presentation, we briefly discuss the 737 manufacturing process at Spirit Boeing Renton for the accident airplane line 8789, the issues that led to this accident, and the FAA's surveillance of the Boeing production certificate. The manufacture of the Boeing 737 aircraft starts at Boeing supplier Spirit Aerosystems. Spirit Aerosystems is a major supplier of 737, 777, and 787 fuselages to the Boeing Company. The company is headquartered in Wichita, Kansas, with facilities in the United States, United Kingdom, France, Malaysia, and Morocco. Spirit Aerosystems manufactures several other key components, including wing leading edges, pylons, nacelles, thrust reversers, and flight deck sections for various Boeing aircraft programs. The 737 airplane fuselages, once finished, are shipped to Boeing via rail to complete the final assembly of the airplane. As part of the 737-9 fuselage build process, edge frames, located by arrows in the photograph, are first attached to the fuselage to provide structure onto which the mid-exit door or MED plug is installed. The edge frame components are manufactured by a Spirit Aerosystems supplier, QuickTech. According to Spirit production documents, the edge frames for the left MED plug were installed on the accident fuselage on June 16th and completed on June 19th, 2023. No document discrepancies were reported on the installation or inspection of the edge frames. After the accident, and upon learning of workmanship issues on the fuselage edge frames for line 8789, Spirit Aerosystems started a review of the QuickTech's manufacturing process, including inspecting all edge frames currently in production and in stock. Further, the company completed inspections of all edge frames in the Spirit production system, including fuselage in the production line. No edge frames exhibited the conditions consistent with those reported by Boeing on the accident airplane. Spirit Aerosystems has design responsibility, which includes the build standard and engineering drawings for the MED plug. The accident airplane's left MED plug was manufactured and completed by Spirit Aerosystems Malaysia on March 24, 2023. The plug was then shipped to Spirit Aerosystems Wichita and received on May 10, 2023. Per Spirit Aerosystems production documents, the left MED plug was installed on the accident airplane on July 18th, inspected and completed on July 28th. A completed installation of the MED plug required the installation of the 4 bolts to prevent upward movement of the plug. Line 8789 departed Spirit Aerosystems via rail on August 20th, 2023. Boeing 737-9 manufacturing build process, there are 10 factory positions referred to as flow days. A simplified version of each flow day can be seen in the graphic. Work scopes associated with the MED plugs, circled in yellow, were accomplished on flow days 1 through 3, 7, and 9. Boeing installation plans, or IPs, are installation instructions for the build of the airplane and have a baseline schedule in the manufacturing process. Nonconformance records, or NCRs, are documents that record discrepancy conditions that can be corrected and meet engineering design. The NCRs are dispositioned with work instruction documents called nonconformance orders, or NCOs. NCRs and their associate NCOs are not pre-planned work and therefore do not have scheduled flow days like IPs. During the investigation, staff heard the term traveled work. According to Boeing, there are 2 types of traveled work. First, where the build article travels from a supplier to Boeing with open work, and second, when the build article moves from flow day to flow day within the factory without the scheduled work being completed. Boeing expects an NCR will be completed on the same flow day it was generated. When this does not occur, Boeing considers this traveled work. According to Spirit Aerosystems documentation, line 8789 did not have a supplier traveled work when it was shipped from Spirit Aerosystems to Boeing Renton. Line 8789 was received by Boeing Renton and entered the final assembly process on August 31st, 2023. On September 1st, 2023, during quality inspection of the fuselage per the IP, Boeing inspectors identified and wrote up discrepancies on 5 rivet locations shown in the photograph on the forward edge frame common to the left MED plug. Boeing inspectors cited that the 5 rivets were not installed properly and needed replacement per Boeing specifications. Spirit Aerosystems manufacturing personnel stationed in Renton were tasked to replace the 5 rivets. To replace the 5 rivets, the left MED plug would need to be opened to gain access. According to Boeing procedures, Spirit Aerosystems manufacturing personnel were not allowed to open previously completed installations on the airplane. Therefore, it would be Boeing's responsibility to provide access to the edge frame. To access the edge frame rivets, Boeing manufacturing door personnel would need to open the left MED plug, which required the removal of the 4 bolts to prevent upward movement of the plug. Once the rivets were replaced by Spirit Aerosystems personnel, Boeing Quality Assurance would inspect the work, and again, Boeing manufacturing door personnel would be responsible for closing the plug and installing the previously removed hardware. The NCR and the NCO to replace the 5 rivets were signed off on September 19th, 2023. Additionally, staff reviewed the IPs, NCR, NCO, and related process documents for the area around the left MED plug on line 8789. Flow days 1 through 3 have scheduled work to accomplish IPs OK to install blankets and install blankets. IP OK to install blankets contains steps to inspect the entire installation area for workmanship discrepancies. IP install blankets contains steps to install blankets for the left aft portion of the fuselage, which included the area around the left MED plug. As previously discussed, during the accomplishment of IP OK to install blankets, Boeing Quality identified and initiated NCR documentation to replacement of the 5 rivets. The NCR rework was linked to the IP prevention and IP for being closed, preventing the IP to be being closed. Each operation step in this IP should have been short stamped. A short stamp is an application of the stamp in the paperwork indicating further work needed to be accomplished. With the paperwork short stamped and the NCR work completed on September 19th, Boeing manufacturing personnel would have had to re-accomplish all work common to the left MED plug area. Staff identified inconsistent application of the short stamp process on IP documents in the work area common to the left MED plug on line 8789. IP documentation, such as the installation of the left interior sidewall panels, were properly short stamped to complete the sidewall installation. Other IPs, including OK to install blankets and install blankets, were improperly short stamped or completely signed off. Staff has proposed a recommendation in this area. Per Boeing's Business Process Instructions, or BPI, titled Perform Part or Assembly Removal, opening and closing of the MED plug would have required a removal document to be initiated. After an extensive search, Boeing and the investigative group determined when work associated with the replacement of the 5 rivets were performed, no removal documentation was created as required by Boeing procedures. Why is this important in this accident? A removal document would have provided pertinent information related to the opening, removing, partially removing, loosening, or disassembling a previously installed and accepted component, part, or assembly. A removal document also ensures that disturbed installations are restored and re-inspected by Boeing Quality Assurance. The failure to generate a removal document on line 8789 resulted in an incomplete left MED plug installation in which the 4 bolts to prevent upward movement of the plug were not reinstalled. Due to the lack of the removal document, the investigative group narrowed the time frame from when the left MED plug was opened and closed during the rework process. A timeline was developed for a variety of sources, including interviews and written statements from manufacturing personnel, Shipside Action Tracker, aircraft build records, Boeing communications, airplane entry and exit records, and photographs from both Spirit and Boeing employees. According to Boeing documents, the rework to replace the rivets on the left MED plug started on September 18, 2023. The timeline showed that the left MED plug was still in the closed position on September 18th until about 7:58 a.m. Investigators could not determine the status of the MED plug between 7:59 a.m. to 10:52 a.m. The evidence showed that from September 18th at 10:53 a.m. to September 19th at 5:09 p.m., the MED plug was open. On September 19th, from 5:10 p.m. to 6:38 p.m., investigators could not determine the status of the MED plug. Photographic evidence showed that on September 19th at 6:39 p.m., the left MED plug was in the closed position. The lack of removal documentation for the work led staff to further review BPI perform part or assembly removal. This BPI was applicable to not only the 737 production line, but also the rest of Boeing's commercial product lines. The review of the BPI revealed 11 notable revisions to the document from 2013 through 2023. During the same period, multiple quality alerts were sent to personnel to reinforce the BPI. Additionally, from 2018 to 2023, there were 16 regulatory compliance issues cited by Boeing, internal audits, and the FAA. In each of these cases, Boeing had initiated safety risk management activities using the Boeing problem-solving model to identify the root cause and potential changes to the process. It was evident to staff that past safety risk management processes regarding this issue were ineffective due to the repetitive findings for this BPI. Staff has proposed recommendations in this area. As part of the investigation, staff conducted a review of the FAA's surveillance of the Boeing production certificate. Each year, the FAA develops a certificate management plan to assist the principal inspectors in planning and tracking the performance of ongoing certificate management responsibilities. A risk-based resource targeting assessment tool was used to assign risk to production holders according to the likelihood that it would produce non-conforming products, articles, or parts. FAA management then developed a certificate management plan for each inspector using the Aircraft Certification Audit Information System. Interviews with the FAA inspectors revealed they were unaware how risks were assessed to determine what additional relevant audits were required in the surveillance of the Boeing certificate. The FAA's compliance enforcement program allows production approval holders to self-disclose their violations, other safety discrepancies to the FAA, and to promptly take corrective actions to prevent future violations. Per the FAA Records Management Order, records of these safety discrepancies were destroyed at the earliest 5 years after closure. Staff determined there was a high probability that historic systemic noncompliance issues were not accounted for when developing the next fiscal year's surveillance plan for the Boeing company and its suppliers. As previously discussed, repetitive systemic issues with BPI performed part or assembly removal have been ongoing since 2018 across all Boeing manufacturing lines. Staff concluded that the FAA's compliance enforcement system, current surveillance process, procedures, and recording systems were not effective in identifying repetitive and systemic discrepancies and nonconformance in the Boeing production system. Staff has proposed a recommendation in this area. This concludes my presentation, and Dr. Woods will now discuss seaman performance issues in this accident.
Good morning, Chairwoman Hamady and members of the board. I plan to briefly discuss Boeing 737 manufacturing personnel experience levels, door manufacturing personnel at the Renton factory, door technician training, and Boeing quality and safety management systems specific to the accident airplane. In 2018 and 2019, following two 737-8 MAX accidents, a decrease in 737 production necessitated the reallocation of personnel and effectively halted hiring. The subsequent global pandemic saw the loss of even more production personnel, particularly among those who were retirement eligible. In 2022, when Boeing sought to increase production back to pre-2018 levels, they also increased hiring. Many of the personnel that were hired came from non-manufacturing sources, resulted in Boeing having a production workforce that had less manufacturing experience than before. Boeing did not conduct a change management or risk assessment on the changes in the workforce, and therefore missed the opportunity to identify the risk associated with having a relatively inexperienced production workforce prior to their introduction to the factory floor. At the time the accident aircraft was in production, 737 door manufacturing personnel at the Renton factory consisted of 1 manager and 24 technicians. The technicians were typically divided into 2 teams named the door crew and door masters. All door personnel typically worked first shift Monday through Friday. Door crew would typically work flow days 1, 2, and 3, while door masters typically worked flow days 7, 9, 10, and the ramp areas. All door technicians, regardless of assigned team, were responsible for functional and operational checks and troubleshooting for all door systems. Staff reviewed Boeing's training program specific to the door personnel. All newly hired production employees were required to attend and pass a proficiency check for their initial foundational training before going on to their job series specific on-the-job or OJT training. At the time the accident aircraft was in production, Boeing did not require a task list, grading structure, or training documentation for the OJT. The OJT program often relied upon the expertise of the more experienced to train the less experienced. For door manufacturing personnel, OJT would have focused on performing routine tasks required for every build. Non-routine tasks, such as the removal of an MED plug, did not offer many opportunities for training due to the task's rare occurrence. During the window the left MED plug was determined to have been opened, there were 4 door personnel identified as having worked on the accident fuselage. All 4 had less than 2 years of experience working 737 door systems. Staff has proposed recommendations in this area. Quality management sets the standards by which a part or component is to meet its regulatory certification requirements and the needs of the customer. According to their quality manual, Boeing's quality management system was the organizational structure, processes, procedures, records, and resources needed to integrate, document, implement, and maintain the various components of an effective business system. Boeing's production certificate contained their authorization to manufacture type certificated products and was audited in 2023 by the FAA. Boeing's QMS manual defined a quality escape as a product or article that did not conform to its approved design and had been released from the quality system. The quality escape section of Boeing's QMS described how to identify, control, document, and disposition a product that did not conform to specifications, regardless of whether the non-conforming product or service was generated internally, received from an external provider, or identified by the customer. However, the manual did not specifically address escapes that were the direct result of human error, nor did it provide guidance for human factors analyses. Staff has proposed a recommendation in this area. A safety management system is a systematic, proactive approach to managing safety risks within an organization. At the time of the accident airplane's production, there was no regulatory requirement for Boeing to have an SMS. However, in December 2015, the FAA had required Boeing to create an SMS as part of a settlement agreement developed to address multiple alleged quality and certification lapses. In December 2020, the FAA accepted Boeing's Voluntary Safety Management System, or VSMS, and it became operational in June 2021. According to Boeing's VSMS manual, the program's goal was to identify, assess, and control hazards and mitigate risks based on a thorough understanding of the systems, processes, human factors, and operating environment. On April 26, 2024, the FAA published its final rule requiring production certificate holders to implement a regulatory SMS. The rule became effective May 28, 2024, with most organizations, to include Boeing, required to comply within 36 months. An SMS is composed of 4 pillars: safety policy, safety risk management, safety assurance, and safety promotion. At the time of the accident, Boeing had not yet fully implemented its VSMS to the Boeing 737 production level, but was working to integrate SMS principles into its QMS while awaiting the FAA's final rule regarding SMS for manufacturing. This integration included having identified the need for and commencing 2 different safety risk management assessments on technician training and the ongoing issues with the removal process, respectively. The SRMs had not yet concluded at the time the accident occurred. After the accident, and in response to a request from the FAA, Boeing developed their product safety and quality plan that identified 6 key performance indicators of production health that would trigger future SRMs should the indicators fall outside their respective control limits. None of the factory-level personnel NTSB staff interviewed were able to describe what an SMS or hazard identification was, what Boeing's safety policy dictated, nor could they define safety culture. For there to be continuous improvement at Boeing, production line personnel must recognize their shared responsibility in supporting a positive safety culture and identifying hazards and risks. Feedback about safety culture elements was a mix of positive attributes, such as technicians saying they were comfortable taking issues to their managers and were never being pressured to do something they did not know how to do, and negative attributes, such as concerns over being labeled a troublemaker or being reprised against for bringing up problems. Most of the technicians had knowledge that various reporting platforms, such as the Speak Up program, existed, though few used them, preferring to talk to their immediate supervisor instead. Data was only collected from the individuals who were selected as possibly being able to contribute information specific to the accident investigation. The NTSB originally decided to initiate the development of a survey to perform a more robust safety culture assessment. However, 737 production was effectively halted due to a work stoppage in late September 2024. In December 2024, staff further determined that the results of any survey conducted at this point would not give an accurate depiction of the safety culture that existed in September 2023 when the accident airplane was being manufactured. The combination of this fact and due to the ongoing work stoppage, it was therefore decided against administering the survey. Although the NTSB was unable to methodically assess whether safety culture elements may have affected the production of the accident airplane's fuselage, the NTSB remains concerned about the impact affirming a positive safety culture has on identifying potential hazards and building effective risk mitigations at Boeing for the future. Therefore, staff has proposed a recommendation regarding this issue. This concludes my presentation, and now we will hear from Mr. Cruikshanks discussing structures.
Good morning, Chairwoman Hamady and members of the board. My presentation will discuss the airworthiness directive issued by the FAA after the accident and post-accident changes to prevent future mid-exit door plug departures. Immediately after the accident, on January 6, 2024, the FAA issued an emergency airworthiness directive that prohibited further flight of all Boeing 737-9 airplanes equipped with MED plugs until those plugs could be inspected and any discrepancies corrected. Results from the inspections showed that all airplanes inspected had plugs that were correctly engaged with the stop fittings, and the 2 upper guide track bolts and 2 vertical movement arrestor bolts were installed. As a temporary solution for in-production airplanes, the FAA approved a multi-airplane non-conformance record on March 1st, 2024, to incorporate the AD inspection procedures on airplanes in the factory. At the completion of the inspection, an entry was made in the logbook to document compliance with the AD. As a permanent solution, on November 4th, 2024, the FAA approved 2 Boeing installation plans, or IPs, 1 each for the left and right MED plugs. The IPs added an inspection procedure in the factory to ensure that the 2 upper guide track bolts and 2 vertical movement arrestor bolts were installed properly. Incorporation of the IPs on the production line complies with the AD and becomes part of the type design of each airplane. Since the accident, Boeing and Spirit Aerosystems have developed a design enhancement for installation on all MED plugs. The design enhancement adds a secondary retention device to the forward and aft sides of the plug below the 3rd stop fitting from the top at locations 1 and 2. The hammer-shaped secondary retention devices must be rotated into position when completing the installation of the plug and would engage with the fuselage stop fittings, preventing vertical translation of the plug. The design of the retention devices would prevent installation of the cabin sidewall panels unless the devices were properly engaged. Additionally, lanyards would be installed on the 2 upper guide track bolts at locations 3 and 4 and the 2 vertical movement arrestor bolts at locations 5 and 6 to permanently secure the bolts to the plug. The bolts with lanyards will provide a visual indication that they are not installed. As of June 2025, the engineering for the design enhancement has been completed, and Boeing and Spirit are continuing certification planning and compliance work that includes notification to the FAA. Once the enhancement is certified, Boeing has stated that they will be installed on all new production airplanes in the factory and a service bulletin will be issued to retrofit the fleet. Staff have proposed recommendations in this area. This concludes my presentation. Next, Captain Blum will discuss operational factors.
Good morning, Chairwoman Hamady and members of the board. My presentation will discuss aspects of operational factors that affected this accident, including flight crew performance, differences in the audio control panel, flight crew training, and Alaska Airlines post-accident safety changes. The crew verified the pressurization was normal while climbing through 10,000 feet. While passing through about 14,800 feet, the left MED plug departed the airplane and the cabin depressurized. The crew described it as an explosive and chaotic experience, stating it was very loud and difficult to hear each other or air traffic control, ATC. The crew promptly proceeded with the memory items on the cabin altitude warning or rapid depressurization checklist, which were donning their oxygen masks and establishing communications with air traffic control. They turned up the volume for the overhead cockpit speakers to hear each other and ATC. The first officer reached for the quick reference checklist, which was not in its holder, so the captain placed the quick reference handbook on the glare shield panel for the first officer, who continued the checklist. The captain began a descent while the first officer ran the checklist and communicated with ATC. The crew heard the interphone chime, and the captain tried to communicate via the cabin interphone with the flight attendants. He reported hearing the flight attendants talking about a hole in the cabin. He attempted to communicate multiple times, but was unsure if they could hear him. One of the flight attendants reported he heard a pilot state the flight was returning to Portland. Around 10,000 feet, the crew took off their oxygen masks and put their headsets back on. They reported a squeal in their headsets, making it impossible to communicate to each other or ATC. The crew took off their headsets and redonned the oxygen masks throughout the approach and landing. The flight crew's response to the emergency was timely, and they landed the airplane uneventfully and safely. Pilots receive hands-on emergency equipment training for the 737-9, -8, and NGs during continuing qualification simulator events every other year. This picture shows the two types of oxygen stowage boxes and oxygen masks in the mock-up trainer located in the simulator facility. The top oxygen stowage mask box, circled in blue, is the one present on the 737-9. In the 737-9, when a pilot pulls the mask out of the stowage box, the oxygen mask microphone is enabled automatically. To reestablish communications with the headset after taking the oxygen mask off, the right door on the stowage box must be closed to stop the flow of oxygen, and the test reset switch, circled in yellow, must be pressed to disable the mask microphone and enables the headset boom microphone. In the Boeing 737NG, there is a mask boom switch, circled in yellow, on the audio control panel to enable either the oxygen mask microphone or the headset microphone. This switch is not present on the 737-9 audio control panel shown on the left. The crew did not shut the right door or depress the test reset switch after removing their oxygen masks. The crew said they instinctively reached for the mask boom switch. Both pilots had more flight time in the NG than the 737-9. Both crew members had one rapid depressurization training event in the simulator during initial training, which was 17 years prior for the captain and 3 years prior for the first officer. When the 737-9 was first delivered to Alaska Airlines, each pilot completed a computer-based training module on oxygen mask systems and communication differences from the NG. As mentioned earlier, pilots receive hands-on emergency training every other year during the continuing qualification simulator evaluation. The captain had the hands-on training 9 months prior, and the first officer 11 months prior to the accident. Staff has proposed one recommendation in this area. Since the accident, Alaska Airlines has made several safety changes. They have updated language concerning oxygen masks and communications in their manuals. They have updated language in their manuals and checklists to remind crews, the flight operations duty officer, dispatch, and maintenance and engineering to pull the CVR and FDR circuit breakers. They have also made several training enhancements to include improved computer-based training slides, a video reenacting a rapid depressurization. They issued a bulletin to all instructors, making communications an emphasis item during training and checking events, and a 2025 simulator training event for all pilots that includes a rapid depressurization requiring reestablishing communications. This concludes my presentation. Thank you.
All right. You're good?
Madam Chairwoman, that concludes staff's presentations, and we are now ready to answer your questions.
Thank you. Thank you so much, Mr. Brazy, Mr. Cruz, Dr. Woods, Mr. Cruikshanks, and Captain Blum, certainly for those excellent presentations, and thank you to the entire staff for your work. We are going to turn to board member questions. Before I do that, after this first round of questions, we're going to take a brief break. We'll come back for the other rounds of questions. Just for the audience, at some point later, we'll have just to set expectations, we will have a lunch break if we continue, and then we'll have more breaks as needed. Staff should feel free to text if you need a break that is not already anticipated. All right, starting with board member questions focused on the major safety issues we identified in this investigation. In the first round, we'll discuss structures to include the mid-exit door plug, not the design enhancement. We're going to talk about that under safety changes. But we'll talk about structures, including the mid-exit door plug. We'll talk about cabin pressure controller and the flight deck door, which with that, I'm going to start with Member Graham.
Thank you, Chair. I want to commend the staff for the great work on the investigation and the draft report. Let's start with the movement of the plug prior to the accident flight. Can you explain how the team determined how much the plug was moving and everything it used to determine that it was moving?
Mr. Fox will answer that question.
Yeah, we did made a careful assessment as we were examining the components. Initially on the airplane itself, we were looking at the stop fittings and looking at damage patterns on those stop fittings that indicated that the plug had moved upward and was translating outboard. And then once we found the plug, we found corresponding damage on the plug itself that made it up to that damage that we saw on the frame. So that told us how the plug was moving up and moving outboard. And then we also, as we were examining the plug, we found some indications of linear features. Yeah, if we can pull up the backup slide, the earlier one. Yeah, the first one. That's the one. So at the top end of the plug, where the seal contacts the plug, you can see those multiple lines of that going across the surface there. That's an indication that the plug was moving up over time. That's a combination of dirt and petroleum jelly that's used as a lubricant on the seal. And so as the plug was moving up, it'd leave a little trace of dirt at the upper edge of the seal at each of those positions as it was translating upward. So that's our indication that it was happening a little bit over time.
Great, thank you for that. Was there anything we got off the quick access recorder that helped with this?
We asked, excuse me. We asked Boeing to take a look at the 9 flights that were on the QAR, and they performed a dynamic loads analysis on the plug structure We weren't really able to determine. We found a couple of flights where it may have moved, but there wasn't a real good indication of that movement over time, only because we had 9 flights.
Great, thank you for that. That's great work. Let's talk about the bolts on the plug. It was determined that even one bolt properly installed would have prevented the mid-flight separation of the plug. Is that correct?
Yeah, again, Boeing, we asked them to do an engineering evaluation of the design of the plug, and that evaluation determined that one of the vertical movement arrestor bolts on the lower part of the plug, one of them would hold it in position, or both of the upper guide track bolts would hold it in position.
Okay, so why was it designed for 4 bolts then?
Redundancy.
Redundancy, correct. That's why we have a great safety record in aviation, because of redundancy and training. At the time of the accident, or after the accident, did we determine, the AD went out, were all the other 737s that were inspected, did they all have the bolts in place correctly?
The AD showed that every airplane had the bolts installed. Some of them had an incorrect number of washers. Some of them had an incorrect torque on some of the bolts, but the bolts were installed on every other airplane.
They're all installed. Do we know how many aircraft that was? Roughly?
I don't recall off the top of my head. I can find that.
Okay. Since this was delivered without the bolts, according to what the team has presented here, at what point would Alaska Airlines have determined that the bolts were missing? What inspection or anything else, maintenance, would they have been able to find that the bolts were missing?
The maintenance program has the first inspection of the plug at 24 months, and then a repeat interval of 24 months. So it would have been 2 years before they would ever open that to look at it.
2 years.
Correct.
Okay. Thank you, Chair.
Thank you. Member Chapman?
Thank you, Chair, and thanks to all of you for your outstanding work on this complicated investigation. Mr. Crookshanks, I think this one goes to you. After examining the door plug, how was it determined that the bolts were missing at the time the plug separated from the aircraft?
Well, I can address that from the materials laboratory examination. We took a close look at the bolts, the holes where the bolts should be installed, and we can bring up the backup slide there. And initially on some of the bolts we saw, or around the bolt holes, we saw some indications of oily deposits on the surface mixed with dirt. Indication that there had been something installed there at one time. Like the edge, it was circular, like the edge of a washer. However, it washed right off once we applied an ethanol clean to it, and then once they were clean, the holes were pristine. There was no indication of any kind of bearing contact damage that would say that a bolt was there and broke as a result of the process. There was also no sign of any wear or indication that a bolt had been working loose over time. That was another thing that we looked for. And in the end, we had this, and maybe the next slide as well, where we have the upper guide track bolt hole, and you can see the hole's intact. There's no way a bolt could have been installed in there unless it broke or was never installed. And the condition, we looked closely under the microscopes just to make sure. We also did materials analysis to check for any kind of transfer marks or anything, material transfer to the remaining components, and there was no evidence of contact with those bolts.
Thank you. That's helpful. Sort of looking at the same question, but from the opposite side, how was it determined that the bolts had, in fact, been installed at one point?
So we had a couple things. The first thing was that there were some paint material, I would say like a greasy material that matched the outline of the washers that we'd expect to be there, and we saw that initially. And then we have the photographic evidence that, once the part arrived at Renton facility, we have photos showing that, and in those photos, you can see that the hardware was installed at that point.
Thank you. And we were told here just in response to Member Graham's questions that fewer than 4 bolts would have been sufficient to hold the plug in place, correct? In fact,
Yes.
possibly as little as 1 bolt would have been enough.
Correct.
And without the bolts in place, what kept the door plug in place and prevented it from separating from the fuselage sooner?
Maybe I'll let Mr. Cruikshanks talk about that.
So the plug was engaged with 12 stop fittings around the periphery, and while the airplane was pressurized, it was being pushed out against those stop fittings, so it wasn't able to move it when it was pressurized. For the parts of the flight that were unpressurized, it was simply the friction between the stop pads and the stop fittings.
And those fittings essentially fit over each other like this, and what was happening is it was gradually moving up, and eventually it wouldn't hold it any further. Is that correct?
That is correct, yeah. We saw the evidence of that in the materials lab exam and those seal marks. And we know that it moved incrementally up over time until it got to an instability point and was able to pop out of the fuselage.
Great, thank you. Chair, I have one additional question in this area. I'll save that for the next round.
Great. Member Inman.
Great. If we could I ask the operator to bring back up slide 41 of the staff presentation? Now everybody's reaching for it. Wanted to know which one it was. This is the timeline of the MED plug. And I'm curious because we saw this just a little bit after our staff meetings. Or on the final slide, it looks like the text there says, "All done. Train your team to do these small installs." What was that correspondence and what was it about?
Member Inman, that correspondence was between the installation manager and the interiors manager. And the interiors manager, after the plug was confirmed closed, had asked the installation manager to have some of his folks travel down to float A10 from float A1 to restore the installation back over the MED plug.
And so that correspondence was only, so what were they asking to train their team about?
Installing just a few pieces of insulation rather than pulling people off of float A1 who were installing the insulation throughout the entire airplane. They didn't want to have those people stop to walk down to float A10 to put three or four pieces of insulation in place. He was just saying, train your people to do it, so I don't have to interrupt my folks.
Is this anything typical we found that they're teaching? I guess I'm kind of concerned. In a text message, one team is telling another team to train their people to do something. That doesn't sound like a documented process.
It is not.
Okay, thanks. I'm going to go on to just about door plugs in general, and I know we touched on this a little bit during the hearing. You know, we found through this investigation that most of the Boeing personnel were unfamiliar with the process of removing and installing a MED plug. Why are we putting MED plugs into airplane fuselages?
They're a alternate method to close a hole that would have been occupied by an emergency exit for seating configurations that don't require that emergency exit. And it's a customer option. They are less complex, they weigh less, and they require less maintenance.
So, but why is the hole in the fuselage to begin with then?
To provide an emergency exit function for airplanes with enough seats that need an additional emergency exit beyond the ones that are already functional.
So is it right to assume that they're manufacturing the fuselage so that they can use a more standardized fuselage and just sell it to different customers based upon what they want?
Customers can choose whether they want to have those exit doors functioning or not, and it's usually based on seating configuration, which would dictate whether or not an additional exit is required or isn't.
Yeah, and it sounds like it's also in order to make sure it's still within the certification, the original certification of the plane? Does that make sense?
So maybe I can help explain this. The 737-9 fuselage can be certified for several different passenger seating configurations. Once you get above a certain number, I think it's 179, you have to have additional emergency exits on the fuselage. So Alaska Airlines does not buy that option. They have a much lower seating configuration than some other airplanes. So they decided to choose the plug option, which plugs that hole, doesn't use as much weight, not as complex. There's several other airlines that also have a plug, United, Copa, Aeromexico.
I guess the question is, why is it safer to manufacture one fuselage with holes in it and then plug it, or another fuselage that just has emergency exits?
The fuselage itself is the same length, and so you've got to have those openings there in case you want that more dense seating configuration.
It gives you an opportunity to sell more airplanes to more
Correct.
people.
Yes.
That's kind of the point I think I
Okay.
was getting to.
Yeah. One fuselage, you can sell it as a couple of different configurations.
In every different configuration you put in, you can inject additional risk into the manufacturing process. And I think we've saw that.
I don't know that we have an exact answer to that question.
It's okay, Doug. You don't have to. I think I'm out of time for this round.
Thank you. Mr. Cruikshanks, the investigation found the airplane had experienced how many flights at the time of the accident where you determined where the door plug was expelled?
The aircraft had accrued 154 flights when the door plug popped out.
Okay, thank you. Mr. Fox, you talked about your analysis, but not a lot of people in the public have visibility to equipment and what we do in the lab. So I was hoping you could take a little bit of time to talk about your very in-depth process. I think there is often afterwards a expectation that you'll know in 5 minutes whether there were, bolts there or not, but it is a very meticulous process, and I want to make sure people appreciate that. So if you could really talk about the expertise of our Office of Research and Engineering, what you have in the lab, along with, I can't leave out Mr. Cruikshanks and Leani here, who isn't with us today. She's out of, not in DC today. But if you could talk about that, I think that would be helpful, including our equipment and needs.
Sure, I can talk to that. It's definitely a process, and the more experience we have, and having experienced people involved in the process definitely helps to identify key features and things of interest. Initially, the visual examination's really an important step in the process, and having an experienced set of eyes, looking for anomalies, things that are different, or looking at those witness marks and things where items are maybe contacting in areas they shouldn't be, and identifying where those are and getting those all documented. Then we move on to the photography documentation there. And then we start looking at things at higher magnification. Initially, with on scene, we're using loop microscopes or magnifiers and things of that nature. Once we get it back into the lab, we have better equipment for doing microscopes and getting optical magnification that way. Then when we need to go to the next level, we're looking at our scanning electron microscope, where we can get magnifications up to 1 million times magnification if we need it. We can also use that same equipment to analyze the composition of the materials, and if we see material transfer, we're looking at closely at those surfaces to give indications of what different materials might have moved against each other, give additional clues to how things came apart. And then we have also equipment for developing 3D models. And we employed that when looking at the hinges. We noticed that the lower hinges were bent, and we used the 3D scanner to scan that and measure that bend angle in those hinges. And that all came together to show that, yes, this is all damage consistent with the door plug moving up and outboard in the course of the separation and decompression event.
Great, thank you. And I'm going to come back to you in another question, another round, but Mr. Cruikshanks, how was it discovered that Boeing's written system description was wrong on the design production instructions for operators?
I believe NTSB staff found the systems description manual had a typo in it. It was calling for pushing the plug up versus down, and we brought that to the attention of Boeing, and they made a pretty good change quickly to the AMM, and then later that went down into the systems description.
Great. And how about the MOM, the multi-operator message that was in development? I know that there were a number of versions. Did you review the MOM that Boeing sent out? Were there issues?
We did review that, yes. That was an iterative process there right after the accident between the FAA and Boeing, because the FAA had issued the airworthiness directive. Boeing was writing the instructions and working with the FAA to make sure that their instructions would comply with the intent of the AD. And through our party process, we were part of that as well. So all of us were looking at the MOM.
Great. Thank you very much. Member Graham.
Thank you, Chair. Besides the damage to the MED plug frame and the plug itself, was there any other external damage to the aircraft?
There was a scuff in the paint after the door, and there was a marking on the leading edge of the left horizontal stabilizer where it looked like a piece of paper or a piece of documentation had struck it. It did not dent it, it just made an impression, an ink impression on it.
So we were fortunate the plug didn't strike the left horizontal stab or some part of the tail section?
Correct.
Correct, thanks. Let's move to, I see we can talk about the cabin pressure controller and the flight door here. So the flight deck door, let's move to that here for a second. When did Boeing go to the flight deck door as a pressure relief device?
The first time was about 2002. There are other models. This is not on the 737 MAX, but there are other models that use the door as a decompression device, and they were starting around 2002.
Okay, so when did the 737, which derivative did this go to? Is it just the MAX?
Correct, during the certification of the MAX.
Okay, and I believe we found out that there was no information provided to the airline in any of the manuals about this?
That is correct.
That is correct, okay. Since we're going to get pressure controllers, let me move to that here. There's been a lot of discussion out in the public and the press about the auto fail light coming on, especially the previous two flights to the accident flight. Can the team talk a little bit about what they found with the auto fail light and the conclusions that you've drawn from that?
We can. Mr. Hooray can address that question. Right.
Yes, the auto fail light was caused by an intermittent failure within the CPCs, which is the cabin pressure controllers. And we were able to determine through looking at recorded data that these were unrelated to the accident event.
Do we know what failed?
We do. There was a microchip failure. It had an intermittent failure, and it was basically causing a data transmission error within the unit.
Okay. And there are 2 cabin pressure controllers, correct?
Yes, that is correct. So if one cabin pressure controller were to fail, then the other one will automatically take control of the pressurization of the aircraft. And then even if that second one was to fail, it is a triple redundant system. The third layer of that being the pilots can now control manually the system without any cabin pressure control input.
And these controllers alternate each flight, who's in control and who's in the backup, is that correct?
That is correct.
And this, I would assume, is a very common design now for most Part 25 certified aircraft?
It is. Well, it's on all MAXs. I believe the same system is on the NGs. It's the same controllers are used on other
It was
versions
on
of the 737.
business aircraft that I flew also on newer ones like that. Okay, thank you for that. That's all I have in this section.
Member Chapman.
Thank you, Chair. Just a couple of clarifying questions in this area. Turning back to the customer choice of a full exit door versus a door plug, that sort of customer choice is not unusual in terms of a big, complicated aircraft like this. I think there are numerous, probably physical choices that are made, but also choices made with respect to avionics and that sort of thing, correct?
Yes,
Yes,
there are
sir.
several options that the airline can choose for their particular airplane.
And with aircraft, as with a family automobile, it's common, I'm certain, for a standardized frame, essentially, to be capable of being modified for various configurations, and that's what we're looking at here. We have a hole in the standardized fuselage that is closed in a couple of different ways, depending on what the customer choice is.
That is correct.
Thanks. This question, I think, is a little unfair, probably beyond the scope of the investigation, but if there happens to be an answer, it would be helpful. This has to do with the flight deck door, using it as a pressure relief mechanism. I believe you indicated that was around 2002 that was introduced in Boeing.
That's correct on the first Boeing aircraft, but the 737 was during certification of the MAX.
Okay, so this would have been in the wake, this would have been subsequent to the September 11th attacks. And of course, we devoted a lot of resources into hardening the cockpit doors after those attacks. Am I correct in assuming that would have been coordinated in some fashion with TSA or DHS to ensure that they essentially had signed off on that sort of a design?
That's correct. The doors meet all of the current security standards that are required by the
Okay.
door.
Great, that's helpful. Chair, that's all I have in this area.
Thank you. Member Inman.
So in our original discussion, we talked about 10 team members on the door team and then a door team leader, I believe. And in the interviews and transcripts we have, specifically, I think it was said that the other 14 door team members, that they had one person that was the most knowledgeable and relied on them to provide direction for door plugs. But none of them have ever opened an MED plug. Is that accurate?
So the one gentleman who had acknowledged that he'd opened an MED plug multiple times was on vacation and I think literally out of the country at the time this plug was open. Every other person we interviewed and or got a written statement from denied having any knowledge of previous or how, knowing how to open it or any previous training on how to open the MED plug.
So I think we outlined, was there 20 people on the door teams?
24 total.
24 people on the door teams, and one person who's out of the country on vacation is the only one that's ever opened one?
That's what we were told, correct.
Okay. I'll go on to the CPCs for a moment. And I think Member Graham brought up a good question about the faults that had occurred. And I think it was, and as I understand it, this is an asynchronous chip that is installed, that basically there were 10 failure 10 failures in the past, or that we had noted on typical sequences that had occurred where the auto fail light had illuminated. Is that right?
Yes, that's correct. There was a specific signature in the fault codes that we were looking for in the memory of the cabin pressure controller, and we found that on 10 other units.
So in the footnote, it was kind of interesting because it was buried into a footnote, but we found that on those 10, but that was out of 585 CPCs that had been repaired within 2 years?
Yeah, I think it was within 3 years, which I think worked out to be about 200 a year. But to put that in context, there's over 10,000 of those units that are in service. So in that sense, it's a fairly small percentage.
But it's still 580 or 500 over 3 years that are needing to be repaired. Is that I know it's not within the scope of the investigation, but is that systemic for, I know it's a small percentage, but it seems like anyone that would fail would be a problem. So, I mean,
Components fail, right? And that's part of it. And so what we look for is a system that can accept a failure of a unit. And in this case, because it is a triple redundant system, we can accept failures of one component of a CPC. It can fail, the other one automatically takes control. And there's, no issue to the crew. It's honestly probably more of a maintenance concern than it is of a safety concern.
But in this case, the maintenance had not been able to be done for that aircraft in question?
No, the maintenance was done. And in fact, every time there was a auto-fail light, the system had taken off with the system being operational. You cannot take off if the system is not operational. You would have to MEL that system.
MEL being?
You would defer it per the minimum equipment list, which is what MEL stands for.
And so if the CPC fails and is not activating, it can't take off?
Actually, you can. The FAA will allow it to take off with one CPC that's not working because you can you can defer it per the aircraft's minimum equipment list.
But with both failing, you could not take off?
I'm not sure. I'd have to look. I mean, you can still control the pressurization system because you can do it manually. I don't know if the FAA allows you to do that, though.
Okay, that's all I have in this round right now.
Thank you very much. After the accident, there were a lot of questions about work performed at Spirit on the airplane related to the installation of the Wi-Fi system. Was the door plug open during that type of work?
While the airplane was at AAR, they did not open the.
At AAR.
Yeah. They did not open the mid-exit door plug.
Great, thank you, and thank you for clarifying that it was at AAR. The flight deck door on the accident plane was designed to open and relieve pressure in the flight deck. That design serves a safety purpose, but what was missing here is something critical. Communicating that design to the operator, in this case Alaska Airlines, and to flight crews is essential for also ensuring safety. Why is that critical?
It's critical because pilots should know the systems of their airplane and what to expect.
Yeah, and Alaska Airlines did confirm to us that they were unaware. Were the flight crews aware?
No, they were not.
That's important
Yes, it is.
for both cabin crew and the flight deck crew.
Yes, it is.
In this case, one flight attendant was injured when it flew open. Did Boeing give a reason for why they did not provide information on the design of the door to the operators and crew?
In a response, they said that the FCOM was based on the 737NG, and when they created the MAX FCOM, they neglected to add the new procedure, or the system function. The crew procedures remained the same, but they did not update the system description.
Right, and they also cited at one point security reasons, and then we had a or at least I had a conversation with TSA that was not confirmed by TSA. This is not the first time Boeing has made design changes without ensuring the operator and flight crews fully understand those changes, to evaluating potential flight crew responses in the design certification process and evaluating what could happen if a door blows open and putting in place measures to mitigate any potential hazards. Can you give us a brief overview of Boeing's procedures for when they make a design change to an aircraft within their fleet, understanding this was changed earlier, that needs to be brought to the attention of operators and their flight crews?
Yeah, typically, when a change is made, Boeing has many different manuals that they can update depending on what that change is to communicate that change to the operator. In this case, with the door, they should have updated the FCOM, which is the Flight Crew Operations Manual.
And do you know if Boeing evaluated the effects of changing how the door plug, the flight deck door performed in this particular model or the previous model in the certification or production before the change was actually put in place?
So they did some testing. They did laboratory testing, more on the side of functionality of the door to make sure that the door lock mechanism was working properly. But that's the only testing we're aware of.
So no full-scale tests or worst-case scenario and how a flight crew would respond or a cabin crew would respond type testing?
I'm unaware of any testing like that.
Okay, great. Did Boeing, and they did not ensure the manuals or other materials were updated, but now those are updated, correct?
Correct.
Okay, and one last question for Mr. Fox. On June 18th, an article ran on NTSB's intranet, which I thought was excellent, Colleen, entitled Under the Hood Series, How Do We Find Things?, which states, every successful search begins with coordination, bringing together the right data, tools, and experts to act quickly while the trail is still fresh. I do want to thank Colleen for her work in writing the article and her work and the help from the Office of Research and Engineering. Not a lot of people understand how we find things very quickly. I will tell you, being the person who was at the press conference, when I announced what neighborhood it might be in, I feared for that neighborhood and the onslaught of people that would be in it looking for the door plug. But Mr. Fox, can you talk about how we go about calculating, modeling, and using data to narrow the search zone? I think that's not something a lot of people understand, and it is a lot of work. I will put in a plug for Bob's class one more time, who we visited while we were on scene, and Bob has since retired. That was the Catlin Gable School. But if you can talk about how we do that.
Sure. It can be a complex process that is a multidisciplinary effort from engineers, meteorologists, drone pilots, and search teams throughout the process. When something happens in the air, parts can be scattered across miles, and so we need to be able to focus our search and identify areas where items of interest are most likely to be found. So we start with a ballistics analysis, calculation that includes factors such as altitude, airspeed, an incline angle relative to the initial separation. And then to understand the trajectory of those parts as they fall, we're looking at factors such as mass and shape of the part that can affect that trajectory. We get meteorologists involved. They're looking at the winds aloft and giving us that data because those will affect how those parts fall, especially aerodynamic parts that are lighter weight. The wind can carry those. And then in this case, the MAD plug, it has a relatively large surface to volume ratio, so that also gets affected by the winds aloft. Once we do those calculations, it kind of gives us a probability plot of where to focus our search. And then we can get drone pilots involved. We have a drone program. We have 10 pilots that are trained in addition to their normal jobs. They're also out searching overhead, visual scans, and they also can do infrared imaging, which, as parts heat up in the sun, the infrared imaging can help spotlight those parts as in the search. And then eventually we got to get boots on the ground, eyes, in the field, looking for those parts and gathering them up. So we do, have search parties and search patterns that we go with there. And then, of course, the public, they're key, often finding those key parts. It might be months later that a farmer finds something in their field, as they're, harvesting. So, we definitely, especially when things are landing in populated areas, we definitely encourage the public to let us know if they find something. They may have found that key part, and in this case, the MED plug. Before we even finished all the refined calculations, we had a call.
Thank you very much. I will also say thank you to the public on behalf of all of us. After accidents, we often have public participation in helping us, which is why we often ask for people to send in things to witness@ntsb.gov, and just really thank them for their efforts because they are a key partner in our investigations as well. Member Graham, do you have additional questions here? Member Chapman, Member Inman. Okay, we're going to move on to the second round, but before we do that, we're going to take a 10-minute break. We'll come back at 11:25 and begin our second round of questions that are going to focus on manufacturing, human performance, including training and SMS and QMS, and we're going to talk about FAA oversight of Boeing and related safety actions and needs. Thank you.